Hello, everybody. Today, we're going to look at something very important in stats in general. Okay, it's a very, very important topic, and it's so common everywhere that it's like you kind of have to know it. All right, even if you weren't doing mathematical methods. But that being said, let's dive right in. Okay, so let's think of some good example to work with. I'll say you have a test. Okay, your class had a test. Okay, and everyone in the let's just say the whole school took it. Okay, the whole school took this test, and we record everybody's scores. Okay, when you record it and you start plotting it, for it's a continuous random variable, assuming. Okay, you plot it. This is kind of what the score starts to look like. A bit prettier than that. Okay, this is what the score starts to look like. Okay, let me just fix it a little bit around here. Okay, so if I have this, okay, brilliant. Okay, very cool. So this is what your graph, once you collect all the scores and put it into a graph, that's what it starts to look like. Okay, so this looks basically like a bell. It's like a bell shaped. Okay, and this is what we call a normally shaped curve or a normal curve. Okay, now it has a few features that I'll just point out. First of all, it is centered, so the maximum value is at the mean. Okay, it is centered at the mean. Okay, second thing, it is symmetrical about the mean, so the amount of area on this side is equal to the amount of area on that side. Okay, it is symmetrical about the mean as well. Okay, another thing is that the standard deviation here plays a massive role. Okay, so since you've graphed everybody in the school, okay, everybody in the school is here, okay, the standard deviation basically tells you how spread out the scores are. Okay, so the standard deviation, we already know that's what the definition is. It kind of tells you how far everything is from the mean. It tells you what the curve looks like. Okay, so if the standard deviation is very, very far, very, very big, sorry, the values are very, very far from the mean. Okay, so you get a curve that looks, if the mean is like this, a curve that looks a bit more stretched out and wide. Okay, because there are more values further away from the mean. And if you have a small standard deviation, you get something like this because all the values are very, very close to the mean. Okay, so based on the standard deviation, it affects the normal curve. All right, so now back to our example. Okay, you can see that in a scenario like this, you would obviously assume that the most of the people get the average number of scores, which can clearly be seen here. Okay, most people end up in this area. Okay, another thing is some people would score really, really high, but that would be a very small number. Some people would score really, really low, again, a very small number. These sort of characteristics are also shown in the normal curve. Why it is so important? It is because a lot of the naturally occurring stuff are normally distributed or approximately normally distributed. What does it mean to be normally distributed? If you graph it, it ends up being a normal curve. All right, that is what it means to be normally distributed. But a lot of things are like that. Okay, so for example, physical attributes, right, like your height, your weight, all of that stuff, normally distributed. Okay, the masses of things like masses of fruits, or like the length of a height of a tree, all of that normally distributed. Okay, so maybe let's look at another example. Maybe let's say you're sitting there, you start to record how long it takes for a computer to load. Okay, how long it takes for a video to render or something. Okay, I know it's a boring task. You don't actually have to do it, but let's say you record um, loading times. Okay, so obviously, for a computer to load, there are a lot of factors, okay? All of the things have to start up, you have to find all the files, you have to set them up, you have to set up some other stuff, deletes memory, create memory, all of that stuff is happening So there are a lot of factors, okay? But you see that, okay, let me just write down lots of factors, tons and tons of factors. But you see that when you make a lot of measurements, a lot of the values are close to a central mean, okay? Central mean, okay? And there will be a small number of values that are further away from the mean and a small number that are in the opposite direction, further away from the mean, okay? Small number of values are far from the mean. Far from the mean, okay? So, when you again plot that, there will be more values here, less value at the corners, and it ends up being bell shape, okay? So again, something that you can't really expect it to be normally distributed, but then when you do this, you go through the analysis, you make the recordings and stuff, you see that it's normally distributed, okay? So, a lot of things in real life are normally distributed, and that's why it's important to know how it works, okay? So, coming back to our case, as in the course of mathematical methods, it is mainly used for continuous random variables, and it can be used to calculate the probability. So, where that comes in for us is actually normal curves are a very special case of the probability distribution functions we've looked at before. Okay? So it is a very special case, and again, a very common case, that's why it's used so often, of the probability distribution function. So all the same things apply again. The area under the entire curve is 1. If you want to find the area, you integrate it, the mean, the standard deviation, everything applies. Okay? And that is how you go about it. But well, you would be thinking you to get the mean and stuff. Oh well, the mean's given. Get like the probability, you would need the function. That is a bit of a hard request because this is what the function looks like. Okay. So you got your standard deviation, you got pi, you got e, you got mu, your mean, you got another standard deviation, your x's. Yeah, good luck trying to integrate that. That's why all calculators have this built into them that you can use it to find find the probabilities under normal curves. Okay, and you can use it in the opposite way as well, which we'll see in the example questions. How to go from a probability to find out something about the normal curve. Okay, but that is mainly it. Okay, that is pretty much it about normal curves. They are basically probability distribution functions, okay? They just come up a lot more often in a lot of areas, okay? So, that is all good. Let's look at something a bit more exotic, okay? Something that less people know about, less people focus on, okay? This is the hardcore stats. Okay, so we're gonna look at z-scores, okay? And what is that? It is basically having a normal curve and standardizing it. So don't be afraid. I'll take you through it step by step. Okay? So first of all, imagine you did that test that we talked about at the start. Your friend from a different school also did that test. How can you tell who did better? Okay? I mean, you could just compare marks yourself, but say the tests were different, okay? Say people perform differently and stuff like that. How can you compare each other? Okay? So to solve that problem, this is where z-scores and everything comes in. Okay? So to understand why it is, or the idea behind it is to, well, say, to really tell how you performed in a test, you can say you can do this. Instead of comparing your marks, okay, because you don't know how his test was, you can compare. You can compare how far ahead of the mean you were. Okay, you can compare that. So if your school had a mean of 50 and you got 70, okay, and his school had a mean of 60 and he got 60, okay, then he did the average, you did better than average. Get that concept? Let's make it a bit more rigid, okay? So instead of just looking at how far you were, you'll look at how many standard deviations far you were of the mean, okay? So you can say, for example, if your school did 50, did the test and the mean was 50, okay, that is a horrible mu, okay? Mu equals 50, standard deviation equals 10, okay? And again, you got 70 marks, okay? So you had 50 plus 1 standard deviation, 50 plus 2 standard deviations. So you were 2 standard deviations above the mean. And say your friend at a different school did the same thing, his mean was 60, standard deviation was 20, and he got 80. So if you had just compared the marks, you would say he did better. But if you look at this, he was only 1 standard deviation above. So by using our method to compare, which takes in that factor of how hard the test actually was, because you're looking at people, you're looking at what the mean was, you're looking at standard deviation, so you can kind of have an idea of how the test went, how hard it was. Same for the other school, and using all of that information, you can see which one performed better. Obviously you did, because you was 2 standard deviations above. So it is a bit hard to say standard deviations above. So what you say is you call this your z-score. Okay? So this is your z-score. You had a z-score of 2, he had a z-score of 1.5. So z-score is essentially how far ahead you are of the mean. So if for example you get a 1.5 z-score, very good. That is a very, very good score. Okay? If you get negative 1.5, you need some work, okay? You're far behind of the mean. All right, so that is where the z-score comes in. And that is how to, or you can see how that's useful. When you want to compare multiple different normal distributions, you use the z-score, all right? So here is the formula for it. And it's quite intuitive, actually. So it's like, how far are you from the mean, okay? And then it's just, how many standard deviations is that, okay? So that is the formula. Again, for a lot of this, it's just put it into the formula and just write down the answer, okay? Usually, it doesn't get much more complicated than this, okay? That is why you may be feeling like I'm skipping over it or I'm going too fast. But the reason is, in the end, you get to this, and that's kind of the end of the story. But I wanted to give some context as well. Now, if you are feeling a bit scared, that is okay. That is fine. Okay, we'll do the examples, and in those, you'll see how easy it is to use. Okay, so one last thing I wanted to go over is the standard normal distribution. Standard normal distribution. Okay, so this is a standard distribution, I guess. It's basically the mean is 0 and the standard deviation is 1. That is the characteristics of a standard normal distribution. Okay, so basically it is your very, very base distribution, and you can, if you can convert a given normal curve into this normal curve, all right, and you can do the same with another one, then you can compare them that way as well. But this is a bit more complicated and often used a lot less. This is the main idea, okay? And this is what I want you to focus on. Knowing about this is good. Maybe there will be like, what is this? What is the standard normal distribution? But this is kind of all there is to that. This is the goal. That is where you focus. That is where you practice. That's it. All right. So now you know everything about normal curves, z-scores, standard normal curves, anything thrown at you. You got this right in the bag. All right. So that will be all for today. Yeah. Good luck with your practice, and we'll see you in the exercises. Bye bye.